Again, one day, long ago, lots of mathematicians got together and decided, you know what, just to make it a little bit more difficult on people in high school math classrooms, let's make it to where the bottom of a fraction can't be a radical. That way they'll have to work a little bit more. And that's where this comes from, rationalizing the denominator. When you're dealing with, let's go with one of the most common ones, 3 over root 2. The rule is when you're dealing with radicals, the bottom cannot, or excuse me, with dealing with fractions, the bottom cannot be a radical. It's just like leaving a fraction unsimplified. So what do we do to get a radical off the bottom? And again, this is something you saw hopefully last year. Well, I know you did. Last year in Algebra 2. The rule is, and the simple way to do it, to get a radical off the bottom of a fraction, multiply top and bottom of that fraction times that radical. Why is that legal? You've been doing it your whole life. To find a common denominator, let's say I wanted a 6 on bottom, we multiply top and bottom by 3. That changed it to 3 over 6. It's the same thing. You're doing the same thing here. To get a radical off bottom, pick some number. In this case, we're going to use that radical itself. Multiply it times top and bottom. You now have on top, and here's the rule. A number cannot multiply by a radical. You will leave this as 3 times the square root of 2. But you can multiply radicals. The square root of 2 times the square root of 2, if you want to do it the long way, is the square root of 4. The square root of 4 is 2. The way I would like for you to remember it, if you multiply something times itself, you're squaring it. And a square and a square root, they're going to cancel each other out. They're undoing each other. So you're going to end up with that number. Square root of 3 times square root of 3 is 3. Square root of 5 times square root of 5 is 5. It just removes the radical because you're squaring it. So 9 over root 3. To get that square root off the bottom, again, we're going to multiply top and bottom by root 3. Now this one's going to have one extra step. On top, you cannot, somebody will do it, you cannot multiply a number times a radical, so you leave it as 9 times the square root of 3. On bottom, the square root of 3 times the square root of 3 is 3. The same way you cannot multiply a number times a radical, you can't divide a number by a radical. Square root of 3 divided by 3 cannot happen. But you can divide a number by a number. And again, I want to point this out. I can't say it enough. There are no pluses or minuses between that. There's one term on top, there's one term on bottom. You can cancel pieces of those terms. So the 9 and 3 will reduce. 9 divided by 3, you can mark it out. 9 divided by 3 will leave you with 3. So your final answer, 3 root 3. A little bit ugly. Slightly. These are pretty nasty. Let's start out with a little bit simpler one though. Let's do, let me think. Let's do 4 over the cube root of 2. Now you got to be cautious here because you can't work it exactly like the problem I just worked. Because if you worked it like that, you're going to multiply top and bottom by the cube root of 2. And the bottom would turn into the cube root of 4. You still don't know that. Makes sense. You've actually, in essence, you're kind of doing it twice. In order to get rid of a cube root, you're going to have to multiply times the cube root of 2 times the cube root of 2. You got to do it twice because you need something on bottom that you know the cube root of. Or you can think of it like this. And here's how I'd actually rather you think about it. What are some things I know the cube root of? I know the cube root of 1. That doesn't help much. Cube root of 1 is 1. The cube root of, 2 times 2 times 2 is 8. So I know the cube root of 8 is 2. I know the cube root of 3 times 3 times 3 is 3. And I know the cube root, we'll do one more. I know the cube root of 4 times 4 times 4, which is 64, is 4. So what you're wanting to do, and the square roots work the same way. I want to turn the bottom of this fraction into something I know the cube root of. I'd use this one. So let's multiply the bottom by the cube root of 4, and that's perfectly legal as long as you multiply the top times the cube root of 4. Again, this is called rationalizing the denominator, getting the radical off the bottom of that fraction. The top is now 4 times the cube root of 4. The bottom is the cube root of 8. And I said it, but I skipped that step, bless you. The bottom is the cube root of 8, which is 2. Nearly done. Reduce. You can't divide a radical by a number, but you can divide a number by a number. There's no pluses, minuses. You don't have to distribute. 4 divided by 2 is 2. So your final answer, 2 times the cube root of 4. Okay, 4 over root 3. Going back to this. And we've always told you, multiply it times itself. Multiply it times itself. You don't have to. Okay? There's absolutely no reason on this problem to do what I'm about to show you. But I just want you to know your goal, and it's not to multiply it by itself. Your goal is to get something on bottom, which you kind of saw that on that last problem. Get something on bottom you know the square root of. You don't have to multiply the bottom by the square root of 3. If you wanted to, I don't know why, you can multiply it by the square root of 12. For this reason. That would turn the bottom into the square root of 36. You just need something on bottom that you know the square root of. We're just trying to get rid of that radical, okay? And the way we get rid of radicals is by getting something we know the square root of. So if you did it this way, that'd be 4 root 12 on top, which could be cleaned up, by the way, and the square root of 36 on bottom. And you would have more reducing and stuff like that, but I just wanted to point out that you don't necessarily have to multiply times itself. You're just multiplying it by something to get something that you know the square root of. Okay, moving on. What if you're given a binomial, binomial on bottom? 3 minus root 6. If you try to multiply this by root 6, you're in this endless loop, okay? You'll never get out of it. If you multiply this by root 6, well, you're going to have to distribute. You've got 2 terms on bottom. This would turn into 3 times root 6 minus 6. So you still got another root 6. So what would you do? You'd multiply by root 6 again. And that would get rid of the first root 6, but it would tack on one at the end. This endless loop. If you ever have a binomial, and when I say binomial, notice that minus sign's thrown in there now. Anytime you have a binomial containing a radical on bottom and you're trying to get rid of it, here's what you do. You multiply by what's called the conjugate, and I would know what that word means. Because we're going to use it a lot for the rest of the year. The word conjugate. 2 terms are conjugates. 2 binomials are conjugates if the only difference between those binomials is the plus minus signs in the middle. X minus 3, x plus 3. 3 minus root 6, 3 plus root 6. 5 plus 2, 5 minus 2. Those are conjugates of each other. Let me remind you that when you're multiplying conjugates, okay, this is FOIL. X times x would give you x squared. X times positive 3x, or excuse me, positive 3 would give you a positive 3x. Negative 3 times x gives you a negative 3x. And negative 3 times positive 3 would give you a negative 9. Anytime you multiply conjugates, the middle terms always cancel. So did we have to multiply all 4 terms together? No. X times x, 3 times 3. That's all you have to multiply with conjugates. So let's clean this up. And I told you this is legal as long as you do the same thing to the top. All you're doing is changing the fraction. On top, distributive property, 3 times 3 is 9. 3 times root 6, question, is that root 18? Anybody? No. Cannot multiply a number times a radical, so you leave it as 3 root 6. On bottom, if I work this correctly, it should remove all radicals. Help me with it, Savannah. We're only multiplying the first and the last terms because of this whole conjugate rule over here. 3 times 3, Savannah, 9. Negative times a positive is a negative. Savannah, what's root 6 times root 6? Root times. 6 times 6, not 6 plus. So square root of 36, which is 6. Again, rule is when you multiply a radical times itself, it's just that number. Root 6 times root 6 will be just plain 6. So now on top you have 9 plus 3 root 6. Can't point out enough that you have two different terms. On bottom you have 9 minus 6, which is 3. Notice no radical. Got rid of the radical, that was the whole point. Don't leave it there. Distributive property. The distributive property, most of the time when we see distributive property, it's multiplying a number times two things in parentheses. It's not always just that. What you're about to see is also distributive property. There's two terms on top. Both of those terms, separated by a plus sign, is being divided by 3. So divide them each by 3. 9 divided by 3 plus 3 root 6 divided by 3. You can cancel out the 3's and leaves you with just root 6. Something else, we're not going to do it, but since that is the answer, you should be able to, think about this, if 3 divided by 3 root 6 is this, you should be able to multiply, think about it, if 8 divided by 4 is 2, then that means that 2 times 4 must be 8. If 3 divided by 3 minus root 6 is this, then that means that this times 3 minus root 6 should be 3, and you could multiply it back out. Well, actually, we did on bottom here. It is 3. Simplifying radical expressions. Honestly, this next part is super easy. This will go back and just review you on what we just did. But we have pluses and minuses now. That's the difference. Root 20 plus root 5 is not root 25. You cannot add radicals. Okay? Now you can multiply these. Root 20 times root 5 is root 100, but you cannot add them unless you have the same radicand. The number under the radical has to be the same. So do we just say cannot add? No. Watch this. Simplify. Again, hopefully you see like 3/6 here. I got to reduce this. The way that we reduce, we take a radical and we look for one of our perfect radicals. We look for one of our perfect squares. I know the square root of 4, I know the square root of 9, I know the square root of 16, 25, 36, 49, and so on and so forth. Any of those numbers, Skyla, do you see inside the 20 there? That's the square root of 4, good, times the square root of 5. 4 times 5 is 20, so I can split it. I know the square root of 4, mark it out, put a 2 in its place. The square root of 20 is 2 times root 5. So you now have 2 times root 5 plus 1 times root 5. You have 2x plus 1x. It's pretty much, and 2x plus 1x is 3x. 3 root 5. You can only, it's, again, up here that's like having x plus y. You cannot combine x and y's. But once you simplify it, you have 2x plus 1x, which will combine together. A little bit uglier. The third root of 24x. Again, I know the third root of 1, 8, 27, 1, 2, 3, and 64. Dot, dot, dot. That's all we'll need. Let's clean these up. Avery, inside 24, you see any of these numbers? The 8, right? Everybody see that? So I'm going to take that cube root of 24x and I'm going to split it into the cube root of 8 times the cube root of 3x. Cube root. And we know that the cube root of 8 we can mark out is 2. So this first one turns into 2 times the cube root of 3x minus. This one's a little bit tougher, Daniel. 81. Do you see any of these numbers in 81? I know that one's, well, that one's in there, but it's not very helpful. 8 times 10 is 80. 64 is not going to be. What do you think, Daniel? 27 times what? Just give me a guess. There you go. Cube root of 27 times the cube root of 3x. And you can tell by just this part alone, these will be able to combine. Cube root of 27 is 3. So you have 3 times the cube root of 3x. Like terms, that's like having 2y's minus 3y's, which is negative 1y. You don't have to put the 1. And, you know, a lot of these problems, guys, we look at this, and a lot of times we just freak out when we first see it. Okay? A lot of times, the problem's not as difficult as we might tend to make it. It's just, I mean, look at that. You know, you show that to somebody, and they're like, I have no idea. You know, that just looks crazy. Just break it down and think about the rules that you know. Maybe take away the fourth roots and think, well, what if it was just this? What if it was just like the square root of 3 times the square root of 4? Well, what would I do? You know, break it down into something that you've done before. Well, a radical times a radical, we can multiply radicals. It doesn't matter what's underneath there. Okay? If it's the square root of 2 times the square root of 3, that's the square root of 6. You just combine what's underneath. So the fourth root of stuff times the fourth root of stuff is the fourth root of 4 times 12 is 48. Y to the third times y to the second is y to the fifth, which looks a little bit better. But just for review purposes, let's clean that up. Okay. Let's see, can we clean up the fourth root of 48? Can we clean up the fourth root of y to the fifth? And I know we can y to the fifth. Okay, because there's at least 4 y's in there. So here we go. Let's try to list the things that we know the fourth root of. 1. That doesn't help. Okay, 1 times 1 times 1 times 1. 2 times 2 times 2 times 2 would be 16. 3 times 3 times 3 times 3 is the same thing as 9 times 9, which is 81. Already too big. So really the only one that we're going to be able to use there, does 16 work? Anybody? Will 16 go into 48? Yes. So let's split it. Actually, let's split this into 2 separate problems. Let's do the fourth root of 48. And I always do this just for clean purposes. And the fourth root of y to the fifth. And like you said, 16 will work. 16 is located inside 48. So let's split this into the fourth root of 16 times the fourth root of 3. One of them we're going to know the answer to. One of them we can solve. Fourth root of 3, we're going to leave that part. Now the second part, y to the fifth. What are the things that we know? And this confuses people. What I'm about to tell you really confuses people. Fourth roots. What are some things that you know the fourth root of? Do you know the fourth root of y to the first, y to the second, y to the third, y to the fourth, y to the fifth? Which ones do you know the fourth root of? And if you'll think of it like this, a fourth root of a variable is the same thing as that variable to the 1/4 power. So I'm saying what powers, what exponents can you take the 1/4 power of or the fourth root of? What do you think? 2, 3, 4, 5, 6, 7, 8, 9, 10? Which ones? You know the fourth root of y to, say it again? 4. Which other ones? 8, 12, 16, 20. Does that make sense? You're multiplying 1/4 times it. Well, what numbers can you multiply 1/4 by to get clean numbers? Multiples of 4. A fourth of 4 is 1. A fourth of 8 is 2. A fourth of 12 is 3, and so on and so forth. So let's split this into something we know the fourth root of. Let's split it into the fourth root of y to the fourth, which she just told me I knew, times the fourth root of y to the first. Y to the fourth times y to the first is y to the fifth. I can split it. Now let's clean it up. Fourth root of 16 is 2. The fourth root of y to the fourth is y. I don't know this, and I don't know this. And the reason I paused there, I'm not worrying about the absolute value bars from here on out. And I'm not going to be as picky from here on out about absolute value bars. I just wanted to introduce that at first. I don't care about absolute value bars from here on out, because really technically right there you probably needed some absolute value bars. Because the fourth root of y to the fourth, well, if you raise something to the fourth power and then take the fourth root of it, that'll always be positive. Okay, so really technically, yeah, you needed some there, but I'm okay with not putting them for now. That's the fourth root of 3 is left here, and y to the first is left there. That's the cleanup. This was the original answer, and that's, well, I say cleanup. I like the original answer better. But if they say simplify, you're going to have to write it in this way. Okay, next one. Square root of 40 divided by the square root of 5. Here's how a lot of people are going to, if you overthink this problem, here's how you're going to work it. Square root of 40 divided by the square root of 5. And you're going to think to yourself, oh, I've got to get that root off the bottom, right? Division is the same thing as a fraction bar. Please remember that. That's the reason it looks like a fraction, dot over dot. To get a root 5 off the bottom, we're going to multiply top and bottom by root 5. I'm doing this the long way for a reason, I promise. That gives you can multiply a radical times a radical. That's the square root of 200 over square root of 5 times square root of 5 is 5. Man, you're going to kick yourself if you work it like this, right? Square root of 200 on top can be simplified. Allie, what's some radicals that you know that's inside that 200? You know the square root of 4, you know the square root of 9, 16, 25, dot, dot, dot. What's some that you know that's in there? You see any perfect squares in 200? I think $2. Maybe that would help. Huh? 2 times. You said, well, 2 is not a perfect square. We know the square root of 4, square root of 9, square root of 16, square root of 25, square root of 36. What are a perfect square that's inside that you can divide into that 200? Got one? No? Huh? 20? Well, not a perfect square. Help her out, Brianna. You think of any? 200. Yeah. No? I'm just asking which of these numbers will divide into 200. Jordan, 25 will. Why do we know that? 200, think about any time, especially if it ends in 00, think about money. $2. Why will 25 divide into $2? Because there's 8 quarters in a dollar, or 8 quarters in $2. Will 4? Will 4 go into 200? Will 4 go into 20? 5 times, right? So will 4 go into 200? Yeah, 50 times. Do we use 25? Do we use 4? You can. What would you use? 100. Okay, we know the square root of 100. So let's split this into, and watch how I do this because I want you to start doing the same thing. You're big boys and girls. The square root of 200, let's split that into the square root of 100 times the square root of 2. Listen to what I just said. Let's split that into the square root of 100 times the square root of 2. Go straight to your answer. The square root of 100 is 10. Square root of 100 times the square root of 2, that's 10 root 2. Over 5. 10 and 5 reduce to 2 root 2. Well, the other way of working it, we can add radicals and subtract radicals only when the radicand is the same. 3 root 2 plus 4 root 2. 5 root 3 minus 6 root 3. We can multiply or divide them anytime. The square root of 2 times the square root of 3, those aren't the same, but that is the square root of 6. You can multiply them. Can you divide them when they're both radicals? Sure. The square root of 40 divided by the square root of 5 is the square root of 8. That'd been easier. But that's not 2 root 2. Yes, it is. The square root of 8 is the square root of 4 times the square root of 2, which is 2 root 2. It says, write each expression using a single radical symbol. Assume that each variable represents a positive real number. We've got the cube root of 2 times the square root of 3. There's no way you can combine that, right? We've always talked about, well, before you can't multiply a cube root times a square root. You know, how are we going to do this? It's possible. And honestly, it's possible using some basic math. It's not really that advanced if you remember this. The cube root of 2. The bottom number is the radical times the square root of 3. The bottom number is the radical. You can only multiply these if, like I said, it's a square root times a square root. Or if it's a fourth root times a fourth root. That's what we've been doing. Well, here's third root times square root. Everybody's pretty good with fractions, right? Can we make those radicals the same? The third root of 2, we might not make that into a sixth root. Makes sense. Watch this. Common denominator. Between 3 and 2 would be 6. What I'm going to do is I'm going to change both of these to sixth roots. That way we can combine them. The way I'm going to do that, multiply top and bottom by 2. This is the same thing as 2 to the 2/6 power. 3 to the 1/2, multiply top and bottom by 3. Common denominator, that would be 3 to the 3/6 power. Top number is the power, bottom number is the radical. I'm going to actually write this as the sixth root of 2 to the second power. I'm going to write this as the third power, or excuse me, the sixth root of 3 to the third power. Now they'll combine. Basic, that's just basic fractions is all I use there. So can I multiply the third root of 2 times the square root of 3? Yes. And if you type this in, you don't have to. If you type in the third root of 2 into your calculator, it's the exact same thing as the sixth root of 4. Why? Because 1/3 and 2/6 is the same thing. Same thing here. The square root of 3 and the sixth root of 27, same thing. So now that we've got them like this, we can multiply these. That would be the sixth root of 4 times 27 is 108. The third root of y times the fourth root of 2y. Again, we need them to be the same root. So let's write this as y to the 1/3 power times, in parentheses, the whole thing is being raised to the 1/4 power. Brett, I need a common denominator. You're going to change them both to what power, or what root? 12. So y would be, since we're changing it to the 12th root, Colby, help me with that. I need a 12 on bottom. Y to the, good. Everybody good with how we do that? 2y, we also need to change that to the 12th root. Anna Marie, help me with it. I need a 12 on bottom. What are you going to multiply, or what's the top going to be? Multiplied by 3 to give you a 12, right? So the top's now going to be a 3 as well. 3 times 1. Makes sense? So now let's change them back into radical form. Now we can multiply them. That's going to be the 12th root of y to the 4th times the 12th root, and be careful here, you're raising this to the third power. When you raise that to the third power, make sure you raise each of them to the third power. 2 to the third, y to the third, that'd be 8y to the third, which would be the 12th root, and we can multiply them now because you're taking the same root, the 12th root of 8y to the 7. Which, as you're writing that down, by the way, could be written as, you could split it, well, it'd be ugly, because it'd be 8 to the 1/12 and y to the 7/12. I probably wouldn't do that. But you can multiply when you have different indexes there. The square root of the third root of 2. Write this, the cube root of 2 on the inside is 2 to the 1/3 power. You're taking the square root of that. The square root of this is the 1/2 power. So all this is, guys, is 2 to the 1/3 to the 1/2 power. A power to a power, we simply multiply. That'd be 2 to the, multiply tops and bottoms, 2 to the 1/6, which is simply the 6th root of 2. So the square root, and that makes sense to me because you're looking for a number that's going to multiply times itself 3 times to give me 2, and then 2 times to give me that. So you're looking for, in essence, a number that's going to multiply by itself 6 times to give you 2. Okay, real quick, I'm going to go through the basic imaginary, and then that's where I'm stopping. Next objective, and this is just, again, to get you started on the next assignment. Students will work with imaginary powers and perform operations on complex numbers. Powers of I. That's the last thing I'm doing today. Hopefully you learned in Algebra 2. The square root of negative. It's impossible. In the real realm that we've always dealt with, you can't take the square root of a negative. Reason being, a negative times negative is a positive. So how are you going to find something that multiplies to give you a negative 1? Something times itself, because negative 1 times negative 1, that'd be a positive 1. Positive 1 times positive 1 is a positive 1. Oh, well, let's use negative 1 and positive 1. We're looking for a square root, something times itself, not two different numbers. So it's going to be impossible to find two things that multiply times itself to give you negative 1 in the real realm. Our entire lives, beginning from the time that you started counting, you've dealt real. There's another realm of numbers out there. Okay, there's a whole nother world of numbers, and these are called complex numbers. And I've always been amazed by this, and it's just like these evil numbers that nobody knew about that just wreak havoc on our world, and we didn't even know about it until now. And there's so much more that goes into complex numbers. It's amazing. But the complex number system is a combination of real and imaginary. A complex number most of the time looks like this. It'll have a real part, and it'll have an imaginary part. 3 plus 4i, that's a complex number. And that's what we're starting to deal with. And we actually talk a good bit about complex numbers throughout pre-calculus. Your most basic imaginary number, your most basic complex number is this, the square root of negative 1. We call it I. That's what I is. That's the definition, formal definition of I. What is I? The square root of negative 1. Now let's talk about the powers of i's, like I said, and then I'm finished with you. I just told you a while ago, when you multiply a square root times itself, bless you, a square root times itself, square root of 2 times square root of 2 times square root of 2 is 2, because it's the same thing as the square root of 2 squared. What is I squared? That's I to the first. That's our basic one. Let's do I squared. Now I'm going to go through these. You don't have to memorize this process. You're just going to have to know the final product. The I squared would that not be I times I? The square root of negative 1 times the square root of negative 1? That's I squared. And what is the square root of negative? Any radical times itself is just that number. I squared is negative 1. So if you take this imaginary number I was just talking about and you square it, you actually get a real number. Next up, so I squared is negative 1, I to the third power. Here's how I'm going to split that. I'm going to split that into I squared. Using my rules of exponents that we just learned, I can say that I squared times I is I to the third, right? Well, isn't I squared negative 1? So is this not negative 1 times I, which would be negative I? So I to the third power is negative I to the fourth power. I'm going to split that into I squared times I squared using the same rule of exponents. To multiply like bases, you add exponents. 2 plus 2 is 4. So I to the fourth power would be I squared times I squared. Well, is I squared not negative 1? So is this not just negative 1 times negative 1, which is positive 1? So you have I to the second is negative 1, I to the third is negative I to the fourth is positive 1. Let's go further. I to the fifth power. And anytime I use a power bigger than 4, I'm just going to split it into the I to the fourth times whatever. This would be I to the fourth power times I, that's I to the fifth. I to the fourth we just found out was 1, so that's 1 times I, which is just I. I to the sixth would be I to the fourth times I squared. And if you know what I'm doing right now, if you understand what I'm doing, you could, anytime you forget the pattern, you could recreate what I'm doing, and you could figure out the pattern like that. I to the fourth is 1. I to the second is negative 1. 1 times negative 1. 1 times negative 1 is negative 1. And hopefully you see the pattern. I to the seventh will be negative I. I to the eighth will be positive 1. I to the ninth is I. I to the 10th is negative 1. I to the 11th is negative I. I to the 12th is positive 1. The pattern continues on and on and on. Here's how to remember. Multiples of 4, such as I to the 4th, I to the 8th, I to the 12th, I to the 128th power is always 1. And just in case you don't remember, how can you tell if a huge number is a multiple of 4? Like 3,456. Anybody know how to tell if that's a multiple of 4? You could divide by 4. Yeah, y'all have calculators. Just divide by 4. It's the last two digits. All you need to worry about, if the last two, because 4 going to 100, and you can get 100, 200, 300. If you look at the last two digits, and if those last two digits are divisible by 4, the whole number is divisible by 4. So 3,456 is a radical. So what if you did I to the 3,456 power? 1. This is ACT. Okay, this stuff's on there in small amounts. This would be like number 57, 56 on ACT is your imaginary stuff. So how do you do the rest of them? What if it's not a multiple of 4? What if I ask you to find I to the 19th power? What's the pattern? I, negative 1, negative I, positive 1. There's the pattern. Is 19 a multiple of 4? What do you think? Is Trevor 19 a multiple of 4? No. But give me a multiple of 4 really close to 19. Either one. 20. Everybody good with that? I to the 20th power. Now, any multiple of 4 is right here. Here's I to the 20th power. So what's I to the 19th power? Right below it. Negative 1. Or negative I, excuse me. What if I wanted you to do I to the 53rd power? Logan, is 53 a multiple of 4? No, give me one close to it, though. And if you need to, 40, count up from 40. 48, that'll work. Here's I to the 48th. Everybody good with that? All multiples of 4 fall right there. So I to the 48th is here. So this would be 49, 50, 51, 52, 53. You follow that? So I to the 48th power was 1. I to the 49th power. I to the 50th power. I to the 51st, 52nd. I to the 53rd power is just I. Okay. It just repeats. Yes. Yes, you could, here's I to the 1st, 2nd, 3rd, 4th, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The only problem is if I give you something like that, it might take a while. But you can. That's it. It just follows that pattern. Everybody follow that?